All right, if you would, go ahead and get started on your classwork. It is page 67, problems 3 and 7. If you're watching on YouTube, Kendall, pause the video while you work and then resume the video when you're finished. All right, let's go and take a look at problems 3 and 7 from page 67. Problem number 3, read that for us if you would, Audrey.
A tank of compressed oxygen has a volume of 0.40 meters cubed and a pressure of 2.76 e to the 6 pascals. What is the oxygen volume at an atmospheric pressure of 1.013 E5 pascals? Assume constant temperature.
Okay, so we have an oxygen tank, and obviously it's been compressed into that tank. And if we were to release the oxygen out into the atmosphere, how much space would it fill? That's the question. But since it says assume constant temperature, but as we use the combined gas law equation here, Michael,
V3 over T equals V2 P2 over T2.
But since it says assume constant temperature,
you don't have to have a fraction.
yeah, we just forget all about the temperature here and go with just this equation, just Boyle's law, basically. So we take the volume of 0.40 cubic meters, we multiply by the initial pressure at which that volume exists. Finding the new volume, 1.013 E5 pascals, your standard atmospheric pressure. Divide that out, and what do we get for the volume if we were to release this oxygen out into the atmosphere? Audrey?
10.9 meters cubed.
11.
Well, I rounded to 11 for the 2 sig figs, but even before I didn't get 10.9, I got 10.66. I may have misentered something.
10
I got 10.89 grams.
0.4 times 2.766. About 1.013 E5. I got it now, 10.89. So rounded 11 though. Verifying one last thing. Yeah, just 2 sig figs. So 11 cubic meters. It filled 11 cubic meters of gas. Questions on that? All right, and problem number 7. Go and read that for us, Audrey.
A balloon filled to a volume of 1.65 liters at 308 Kelvin is heated to 325 Kelvin. What is the new volume of the balloon? Assume the pressure is constant.
Since it says assume pressure is constant, Michael.
You don't have to do pressure, you just do volume over temperature.
And so basically Charles's law, right? And we plug in the initial volume here of 1.65 liters at a temperature of 308 Kelvin. It's heated up to 325 Kelvin. What should we expect to happen to the volume, class?
To go up.
We should expect it to go up because volume and temperature are directly related. Increased temperature, we should get an increase in volume. Cross multiply the proportion, and what do we get here? Michael?
1.74 liters.
Good, not a huge increase, but 1.74 liters got that as well. Questions on the combined gas law? Yesterday we began talking about Avogadro. Genesis says hi, by the way. I let her know we gave her a shout out on the video. And so anyway, but Avogadro's law. And Avogadro said this: if you have two different gases, whatever they are, who cares, but you have the same volume of gas, maybe you've got a liter of gas, they're both under the same pressure, they're both at the same temperature. What must be true about those two gases, Audrey?
They are equal.
In what way? Obviously equal in volume, temperature, and pressure, but equal in what other way? Michael?
Molecules.
What about the molecules?
Same number.
Same number of molecules. Okay, so same volume, same pressure, same temperature. Those two gases will have?
Equal. The same number of molecules.
Same number of molecules, equal number of molecules. But we can't count individual molecules, so instead we count the number of molecules in what? Class?
Avogadro's number. Mole.
Moles, in moles, right? How many moles of gas do we have? And so one of the things we worked on yesterday was finding, well, what is the molar mass? Because you can find the mass of a gas easily enough, but you can't count individual molecules. So we use Avogadro's number, which is, Michael?
6.02322 times 10 to the 23rd.
There we go. And so we use that, or he used that as his number for a mole. Well, remember, a mole of a gas is going to have the same mass in grams as a molecule would have in atomic mass units. For instance, if I had a nitrogen gas, N2, okay, pure nitrogen, I could find, well, first of all, on the periodic table, I could find the atomic mass of a single nitrogen atom. Can we read from that far? What is the mass of a single nitrogen atom? 14.01 AMUs. But a nitrogen molecule is N2. So the molecular mass of nitrogen is?
28.02.
Because we have two atoms within the molecule. And so then if we had an entire mole, we had 6.022 times 10 to the 23rd molecules of nitrogen. How much would be the mass of that mole of nitrogen gas?
28.02 grams.
All right, so for instance, let's suppose I took a sample of nitrogen, I accounted for the mass of the container and subtracted it out, and I found that my nitrogen had a mass of 17.3 grams. How many moles would that be? Well, what would I have to do? If a mole is 28.02 grams, I have 17.3 grams.
Divide.
Just divide at your seats. How many moles do I have? Call it when you got it.
0.6.
0.617, blah, 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 right? So if we rounded 0.617 moles, a little over half of a mole. Does that make sense? What if I had 58.3 grams? How many moles would that be? And we'll get this from Audrey.
2.08.
Yeah, 2.08 moles. A little more than 2 moles. Make sense? And that's something we're going to have to be able to do as we use what's called the ideal gas law. Next section of notes. The ideal gas law builds on Avogadro's law. And it says, well, if we know that volume, temperature, and pressure, if they are a certain thing, all gases will have the same number of molecules. If that's true, then I should be able to come up with a constant ratio for gas. For gas's pressure, temperature, volume, and number of molecules, if it's always the same. So we have the ideal gas law. Now, the key here is the combined gas law takes a gas and changes something about it. It changes the pressure, or it changes the temperature, or it changes the volume. And we see what other changes happen because of it. The ideal gas law doesn't have a before and after to it. It just says we have this much gas. Given these conditions, what condition are we missing? And it's this PV equals nRT. Your ideal gas law equation is PV equals nRT. P is pressure. And for our purposes, we're going to measure pressure in atmospheres. V, of course, is volume. For our purposes, we'll measure volume in liters of gas. N is simply the number of moles. N stands for number. It's the number of moles. We will need what we did a moment ago with calculating molecular mass, molar mass, and then taking mass that we're given to figure out the number of moles, like we just did. The T, of course, is temperature. We'll have that in Kelvin, just as you would expect. The R is the new letter, right? R is the letter chosen for the universal gas constant. You may be thinking to yourself, why R for a gas constant? I don't know. But it's the letter that was chosen by somebody way smarter than me. And as universal gas constant, you need to memorize this number, 0.0821 liters times atmospheres over Kelvin times moles. You'll notice that these units allow everything to cancel out. On the same side of the equal sign, we have moles and Kelvin. Well, the denominator cancels those away. And in the numerator, we have a liter and atmosphere, which will cancel with the liter and atmosphere on the other side. This is our ideal gas law. Let's look at how we can use the ideal gas law as we look at page 64, example problem 4.6. Page 64, example problem 4.6. Michael, read the problem for us if you would.
The pressure of 52.1 grams of chlorine glass is 6.28 atmospheres at 320 degrees Kelvin. Or 320 Kelvin. What is the volume of the gas?
All right, so we know the pressure, we know the mass, we know the temperature, and we're looking for the volume. Does that make sense? So if we're looking for the volume, we're going to take this ideal gas law. Notice there wasn't a before and after. Nothing changed, right? Something changes, that's combined gas law. Nothing's changing, it's ideal gas law. And we want to get volume by itself. Well, that's not terribly hard. What do I do with this equation to get the V by itself, Michael?
Divide away pressure.
Divide away pressure. So that V equals
nRT over P.
nRT over P. So we just plug in the numbers. We know the pressure, class.
52.1.
Know the pressure. Look at the problem. What is the pressure?
52.1.
No, that's the mass. What's the pressure?
6.2.
Atmospheres. There we go. 6.2 atmospheres. That's your pressure. All right. The temperature.
320.
320 Kelvin. And of course, we know R is always going to be, say it with me, 0.0821 liters times atmospheres over Kelvin times moles. Say it again. 0.0821 liters times atmospheres over Kelvin times moles. Now, here's the next thing. They give us the mass of the gas, because that's how you could measure gas. They tell us we have 52.1 grams of Cl2 gas. But I don't need to know the grams, I need to know how many moles that is, correct? So looking at chlorine, and did you find it already, Audrey? 35.45 AMUs is for an atom. But Cl2 has 2 atoms. So what's a molecule? 70.9 AMUs. Okay, so what's a mole? 70.9 grams. Okay, so 1 mole, 70.9 grams. I have 52.1 grams. How many moles do I have? 0.734 blah, blah, blah. Is that what you got? Put that in the memory of the calculator. All right, so that's going to go in here for the N, the 0.734 blah, blah, blah moles. Now notice what happens with the units. Denominator mole cancels with this mole. Denominator Kelvin cancels with this Kelvin. Denominator atmosphere cancels with this atmosphere. So I'll be left with liters for my volume. Make sense? And so then we just plug in the numbers. We take our memory value, we multiply it by 0.0821, we multiply by 320, and we divide out the 6.2. And what is going to be the volume of this chlorine gas? How many liters will it fill?
3.1.
Good, and round it off. It is 2 sig figs, right? Yeah. So round it off, it is
3.1 liters.
3.1 liters. Do you see how to use the ideal gas law? You're going to be missing something, but somewhere along the line you're going to have to use that atomic mass, molecular mass, molar mass to find the number of moles. Turn over to page 67. Turn over to page 67. Let's look at another problem like this. And go ahead and read number 11 for us, if you would, Audrey.
Find the volume of 50.4 grams of oxygen gas at 740 torr and 273 Kelvin.
All right. So let's take a look at the numbers we're given, first of all. The first number we're given, class,
Volume.
we're not given a volume. It says find the volume. First number we're given?
50.4 grams.
50.4 grams. That's the mass that we're given. That does not fit into the ideal gas law, does it? But we're going to use it to get the number of moles. The mass gives you the number of moles. Eventually, it just takes a little bit of work. By the way, what type of gas is this again? Oxygen. This is O2. Okay, what is the molecular mass of O2? 32. 16 is the atomic mass, so the molecular mass is 32 AMUs, so what's the molar mass?
1.57.
What's the molar mass?
32 grams.
32 grams. Okay, that's 1 mole. 32 grams. I have 50.4 grams, so therefore, how many moles do we have? Michael, you called it out a minute ago.
1.575.
Good, I don't need a memory for that because that came out evenly. All right, do we see how to calculate the number of moles? Any questions on that? From the table, from the periodic table, you get your atomic mass. Figure the molecular mass depending on how many atoms are in the molecule. And once you know molecular mass, you just change it to grams, AMUs to grams, and you've got your molar mass. Oh, you got it now?
Yeah, I did it back.
Okay, did it backwards. Remember, you're gonna always divide by whatever 1 is. So you're dividing by 1, but we call it 32 grams. All right. Let's see the next thing. Next number they give us.
740 torr.
740 torr. So there's my N. What is torr? Pressure. Okay, so my pressure is 740 torr. Questions, comments, thoughts?
You gotta have atmosphere.
I can have atmospheres. Well, what is 1 atmosphere?
760.
So divide by 1, or 760, to get how many atmospheres do we have?
0.973.
Just under 1, right? 0.973, blah, blah, blah. Just under an atmosphere, right? Because 1 atmosphere is 760. We're almost to 760, so we have a little bit less than atmospheric pressure. This I'm going to need a memory for. So put the pressure in the memory. All right, next number they give us.
273 Kelvin.
And that's
Temperature.
temperature. Hey, at least that's already in Kelvin, so I'm good to go with that number. And I'm looking for,
R.
well, I know R as well. Okay, what is R, class?
0.021 liters times ATMs.
There we go. And so I know that number. And I'm looking for the volume again. What is the equation? What is the, first of all, what is the ideal gas law equation, Audrey?
PV equals nRT.
But once again, if we're finding the volume, we're going to rewrite that.
V equals nRT over P.
All right. So we're going to take the N, that's the 1.75, 1.575, yeah, times the R, 0.0821, times the T, 273, and we're going to divide all of that by the P, which is in the memory value. And what is going to be the volume of our gas, Audrey?
I erased my memory on it.
Oh, you erased the memory. Could you do 740 divided by 760 real quick? All right, so run through it again. So we got the N times the R times the T, and divide out your pressure.
Okay.
What do you got?
36.25.
That's what I had also. Okay, and then sig figs for number 11.
3.
So we'll round, Audrey.
36.3
And volume measured in
liters.
liters. That's what you had as well, Michael.
Mm-hmm.
All right, questions on this? Read number 12 if you would, Michael.
Find the pressure of 261 grams of nitrogen gas at 63.2 liters and 350 Kelvin. The molecular mass of nitrogen gas is
Get that right.
0.02 AMU.
Good. All right, notice they gave you the molecular mass already, not the atomic mass, the molecular mass. So we don't need to do doubling or anything. They already doubled for us. Go and do number 12 at your seats. Numero 12. Doce. At your seats. That's a lot of gas. what'd you get?
I got 4.248 grams.
Good. 4.235, blah, 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 rounded off. It looks like, again, 3 figs, yes, so 4.24, and it is pressure measured in atmospheres. And there we go. Is that what you had also? Excellent. Questions at all on the ideal gas law? All right, so again, how are you going to tell? Because that's really the only two equations we've had in this whole chapter, right? Ideal gas law, combined gas law. Right, because Boyle's law, Charles' law, gave us X law. Those all relate to the combined gas law. So if you have something, a before and after, this happens and then the temperature changes. This happens and the pressure changes. This happens and the volume changes. That's combined gas law. If they just say, here's the gas, especially if they're giving you the mass of the gas, that's where you're going to use the ideal gas law. All right? You'll practice with that in your homework tonight. Let's talk about our last section here as we wrap up chapter 4 today. Look at page 64 with me, if you would, please. And we're going to talk about some pneumatic devices. If you get that term in your notes, it starts with a silent P, pneumatic devices. Okay, pneumatic devices are devices which transport air or are driven by air pressure. Devices which transport air or are driven by air pressure. Devices which transport air or are driven by air pressure. Devices which transport air or are driven by air pressure. Let's take a look at some of these pneumatic devices right here in your textbook. The first one I want to look at is actually on page 66, if you'll skip over there. And it's, they call it a compressor, a bicycle pump, right? A ball pump, right? Pump your soccer ball, your volleyball, what have you, your bicycle tire. Really straightforward device. It just has a flexible disc inside. And as you push down, the disc is designed curved in such a way that as you push down, it forces the air down through the pipe, the tube, into the volleyball, into the soccer ball, into the bicycle tire, whatever. But because of its curvature, as you pull it back up, it bends and allows air to flow past it. And as you push it down, it flexes it back out enough and makes a seal. This is why, too, if you play with it too much, you can get it to stop working. Because it's just a flexible disc that can easily deform, and then it's not doing anything for you. I used to use a bicycle pump or soccer pump to demonstrate Boyle's law. How as you press down on the gas, you're increasing the pressure on the gas. And then I broke a couple of pumps that way in consecutive years, and I decided not to do that demonstration anymore because I'm cheap. But really, really basic device, and it transports air. It's a pneumatic device. Flip back, if you would, an exhaust pump. Very similar, but instead of a flexible disc, it has an opening valve. So you see there, if you were to push down on the pump, as you push down, the air that's underneath the piston pops valve 2 up. Does that make sense? As you push down, it also forces valve 1 forward to seal off the tube. So you see how valve 1, as you push down, it's going to push that valve in, and valve 2 can pop open and allow air to rush out. As you push on the air, it kind of pushes on both of the valves. But then as you draw it up, well, the air above the piston is going to force valve 2 to stay closed. And as you draw it up, you're creating a vacuum which allows valve 1 to pop into the low pressure chamber. Well, as it does, air is going to, from the glass bell, is going to rush into that lower chamber. And that's how you force the air out. It's the reverse of a bicycle pump. Instead of pumping air in, you're pumping air out. Questions on the vacuum pump? A basic handheld vacuum pump. Now, a vacuum itself uses these rotating fan blades. And this is true for a ceiling fan as far as moving air. It's true of the, in a sense, of the motor that's inside a vacuum cleaner. It's true of the fan blades in a exhaust fan in a bathroom. The fan blades are angled in such a way that as they spin, they force air one direction. So, for instance, if you've looked at the ceiling fan blades in your house, they're angled slightly. And there's also a switch on the ceiling fan that if you switch it, most of them, if you switch it down, the fan blade will turn a certain direction. So as the fan blades hit the air, the upside hits the air. As it hits the air is forced downward, and it blows down on you, keeps you cool in the summer. In the wintertime, you're supposed to switch that switch to an up position, and the fan will actually spin the other direction. It'll hit the downward side of the blade hitting first, and that forces air upward. That way the air, instead of blowing directly on you, the air is forced up, and it just sort of dissipates around the outside of the room. It still keeps the air moving, but it doesn't make you cold, theoretically. And it helps the heater to circulate warm air in the house and things like that. It sucks up the cold air and pushes it up to the ceiling where the warm air is and allows that to just kind of circulate around the house. Same thing is true with the blades in the vacuum cleaner. They're designed to force the air out of the hose and down into the main chamber where you see the dust spinning around in modern vacuum cleaners, not the kind with the bagless vacuums. And the idea is that creates a suction pull. Okay, same kind of thing. It just uses the fan blades to do it. Same thing with the exhaust fan in a bathroom. Fan blades are angled in such a way that as it spins, the air is forced up and into the attic, so it stinks in the attic. I discovered, by the way, a couple summers ago, it had to be in the summer, right? One of my exhaust fans stopped working. And switch, nope, nothing happened, and check the breaker, motor died. So I'm like, can I buy a replacement motor? Well, a replacement fan's only $20. Just buy a replacement ceiling fan. So I go to swap it out. Well, I had to go up in the attic to swap out the ceiling fan because they had nailed it, not screwed it, in place. And they hadn't done it through the slots that were conveniently provided so you could slide the old unit out and take it out. No, they'd nailed through the metal. So I had to rip those things out. I'm up in the attic sweating to death, getting, insulation all over me. And strategy tip from my dad after the fact, cover yourself with like baby powder or talcum powder or something on your clothes, seal off your pores so fiberglass can't get in because it itches really bad. I know it itches really bad. But anyway, so I discovered this though, that the exhaust vent went right into the insulation. There was nowhere for the stinky air to go. The moist, humid air of a shower, nowhere for it to go, just straight into the insulation. So I ran some ductwork to the end of the house where the vents were, so you could actually vent it out. But anyway, that's free. So those pneumatic devices move air. Other pneumatic devices are driven by air pressure. One of them I think is really cool is one that I use every spring, and that's the sprayer device that you see on the bottom of page 64. I buy the cheap Walmart brand Spectracide weed killer, and I hook up my hose to the weed killer, and the water shoots out. Well, as the water shoots through the sprayer, as it shoots across there, it forces any air that was on the top of that straw that you see there, forces that air away. And because it's moving so fast, the liquid itself has virtually no lateral pressure to speak of. So there's no pressure pushing down the straw. But the bottle has a vent in the cap designed to allow air pressure to push down on the rest of the liquid, and it forces it up the straw. And so that liquid is carried away with the water, and so this concentrated weed killer sprays all over my yard along with the water. And so I'm watering the yard and killing weeds at once. Now I did learn you don't want the spray to hit flowering bushes, because it'll kill whatever side of the flowering bush that it hits, along with weeds. But it's a great way to take care of dandelions. So while everyone else in the neighborhood has dandelions in their yard, mine does not. And the first 10 feet of my neighbor's yard has no dandelions either. The other side of his yard has plenty, but not that side, because I spray it, because I don't want dandelions in my yard, much to Chloe's chagrin. She loves dandelions. They're beautiful. Now, this idea of liquid being sucked up by another moving fluid stream is called entrainment. Entrainment. You could think of entrainment, and this isn't necessarily true, but even the vacuum cleaner, right? There's this moving air stream, and so dust and debris and dirt is sucked up in. It's not quite the same. It really refers to a liquid being sucked up in, right? But the liquid is sucked up into this moving fluid stream and carried right along with it. Entrainment. Fluid caught up and carried along by a nearby fluid stream. Now, Michael mentioned earlier spraying people with his water bottle, so Michael gets volunteered for this next demonstration. And Kendall, I'm sorry, it is not going to show up very well, but kind of a cool demonstration you can do at home. All you need are a couple of straws. I'm going to use small straws here. Come here. Well, actually, Michael can't come here. I'll just aim at Michael. Okay? So basically, this one straw is kind of like the straw that sits, he's wisely closing his books. Can demonstrate, for instance, let me drag it over a little bit more. I think I'm right on the edge of the camera. The straw that goes down into the liquid, the weed killer. This is not weed killer, it's just water, it won't hurt anybody. Now, I'm not going to shoot water through this, but obviously water is what would be shooting through the hose in the case of the weed killer. In this case, I'm just going to use air. And of course, as I blow the air through the straw right across the top of this straw, that takes out the air pressure, which allows water to suck up through the straw and spray all over Michael. Let's see if I can do it. All right. It's worked before. Of course, it's not going to work while it's on YouTube. All right, got a little bit of it. You can see it happening, right? I'm not blowing down. I'm not blowing into the water forcing. I'm just blowing right across the top. I did get a little on his desk. And so the water's just being sucked up the straw right into the moving air stream. Did I get you?
A little bit.
I got really close. Okay, that was great fun. Here, no, I'm just kidding. You don't want to put your mouth on the straw now. But anyway, it's a great thing. You can try it at home sometime. And now this voice hasn't messed. Okay, I'll clean it up. All right. But anyway, I just think it's kind of a neat demonstration, something you can do at home. And so if you feel like doing that with a couple of straws, I cut them down to size to make it a little bit more manageable for the smaller cup. But whatever. Questions on entrainment. Okay, so we got a little bit of a visual and a little bit of a tactile as well, and we had a chance to experience entrainment. All right, another cool device, of course, we looked at this already, though we didn't see all how the pistons inside and valves work, is the lift pump for a well, like maybe the Duke of Tuscany may have had. And we see there a valve 2, and then valve 1. The idea is as you push down, valve 2 pops open. Okay, and as you push down on the piston, or as you lift up on the handle, it pushes down on the piston, and valve 2 pops open, but it forces valve 1 closed. Okay, what that does is it pushes water up above the piston. Then when you push down on the handle, it lifts up on the piston, and valve 2 pops shut, and valve 1 is able to open as atmospheric pressure forces water through valve 1. All you're doing then is you're lifting the water that was sitting on top of the piston up, and as it lifts up, it pours out the spout. Kind of get the idea of the back and forth action there. So again, kind of neat, just a really simple device, uses just a couple of valves and atmospheric pressure and a piston to get that to work. Another one that's kind of interesting is the siphon. Okay, so a siphon, you write that term in your notes if you would. A siphon is a device used to transport liquid, from a higher container to a lower container. A device used to transport liquid from a higher container to a lower container. Device used to transport liquid from a higher container to a lower container. Back in the 70s, gas prices skyrocketed under President Jimmy Carter. Inflation was soaring through the roof. His foreign policy was awful. He tried to appease everybody in the world instead of having a stance of strength. Instead of recognizing America's going to be strong, you don't want to mess with us. He allowed a hostage situation in Iran. There was a lot of bad that happened under President Jimmy Carter. He just didn't know how to run a country. He wasn't a bad man necessarily, just had no clue how to operate a country and manage its economy. Well, as gas prices soared, which back then, hitting $1 a gallon was nuts, okay? People would steal gas out of each other's cars. So if you didn't have gas for your car, you couldn't afford the gas, and there were long lines, there was no gas to be had, so prices went up, supply and demand. But also, there just wasn't gas to be had in America, and so, hey, I'm going to get gas out of his car, and so people would take a tube, push it down into the gas tank, put their gas can underneath, and they would suck the air out of the tube. Well, as they sucked the air out of the tube, that allowed atmospheric pressure, air pressure that was in the gas tank, to push the gas up the tube and down. Now, if you're looking at the picture of the siphon, picture the higher container being the gas tank, picture the lower container being the gas can. You can suck the air out and you'll cause the liquid to start rising in the tube. But if you take the suction off, air pressure that enters the tube will just push the gas right back down. Well, if you can get the gas to rise up the first tube to point B, continue coming across to point C, and you can get the column of gas to come down just beyond point D, you now have a column of water in each side of the tube. And if the column inside D is heavier because there's more of it, it'll start to fall. Well, as it falls, there would be created a vacuum, low pressure. Air pressure pushes down, forces the water to just keep draining. So you don't get a huge mouthful of gas necessarily, just get a little bit of gas in your mouth, which is a bit unfortunate, but after that the gas will just drain all the way out. I've done this with, I had a swimming pool on my deck, and instead, because I'm a nerd, instead of just, well, not the fact that I had a swimming pool on the deck, but instead of like just dumping it out or pushing one side down to allow it to drain out, I used a garden hose. And because I'm a nerd, I had one end there, and then I put the other end down below the deck, sucked the air out of the hose, and allowed it just to drain away. I showed my kids, and they didn't care. We can do this demonstration as well here with just a couple of cups. So we'll let this cup, of course, be the higher container, and we will empty this person's gas tank. I don't actually, this is stealing, by the way. If you steal from gas, I don't do this. But we're going to allow the liquid here to drain away. And I think I may want the longer tube down here. So we're going to drain as much of this out as we can. And so all I got to do is suck just enough air out. And it just keeps flowing and flowing and flowing until it reaches the bottom of the tube. And once it reaches the bottom of the tube, air enters the pipe, and I've got all the gas. Not all the gas, I should say. Of course, we could flip it around and put it back in. Now, I want to show you something interesting here. Notice there's still water in the tube here. So it begins to drain. Now watch what happens. See how it keeps leveling back out? Water seeks its own level even when it's an overhead connector joining the two of them. It's kind of a neat thing there. All I did here was I took two flexible straws and I kind of wedged the one straw into the other. Now that pinch wasn't a perfect seal, so then what I did was I melted some extra candle wax. You know how candles sometimes, like the inside of the candle gets burned way down? Just chopped the top off of that candle and I melted it, and then I dipped this part down into the wax and allowed it to seal everything off. So again, something just kind of homemade there. But a neat demonstration too, you can see how air pressure just pushing down causes the liquid to drain out. So again, because it uses air pressure, it's a pneumatic device. It's not transporting air, but it uses air pressure. All right, tomorrow we're going to have a quiz over chapter 4. So your homework tonight is study chapter 4, and to help you be ready, I've got a handout for the math. Okay, so Kendall and anyone else watching on YouTube, there is a handout in the description of the video, a link to the Dropbox file. So that handout will practice the math. You review over the terms. We'll review in class tomorrow as well. We'll also go over the handouts, of course. Make sure you're ready. Once we've reviewed, we'll go over the quiz. We'll give the quiz. Tuesday, that's lesson 26. Tuesday, lesson 26 will be your next test. It'll be over chapters 3 and 4. Test coming up Tuesday, lesson 26 over chapters 3 and 4. So liquids and gases, your fluids, will be in on that test. Are there any questions on what we talked about today? All right, have a wonderful rest of your day, and you are dismissed.